Hello students, so I am doing this official recording to just make sure that I handle this question for the Ntobolo village thing uh, in a more like sort of like in a more open manner, yeah, so that I actually do not have to get a lot of queries and the like. It is due tomorrow. So tomorrow you are submitting. Make sure you do submit. Tomorrow you are submitting this assignment. So let me just bring about the data that I have. So So this is the data that I have for my question concerning Ntowolo village. Okay, that's the data there. Yes, this is the data. I can't even zoom it. So I have, as you can see from here, getting these things. Let's see if we can get it a little. Come here and okay. So what do we have here? What we are saying is that from my question, there's of course a storyline there, but I need this information. The length of the slab, which is that one there. The weight of the slab, which is this one, 4.72. Then the mu, which is in this case URD between the rope and the pulley, 0.56. Between the rope and pulley E, this is for pulley D, this is for pulley E, 0.46. Between the rope and pulley F, it is 0.52. And then between the wedge and the slab, which is the bridge deck, it is that 0.05. And then between the wedge and the ground is 0.28. And then between the tires and the ground, which is TH, according to vehicle tires and the ground, it's 0.71. Wedge angle is 32. And then the what's this? The angle AB, which is AB, in this case it is ABD. It's 64 degrees. And then the weight of the wedge itself is 23, in this case kilonewtons. So the first question we did it in class. I don't think there was anything. We were just supposed to find, we are given this is 64 degrees. Okay. So we were just supposed to find the tension there after calculating the total weight of that. So we had calculated the total weight of this beam to be let me see. The total weight we had calculated was, we did it in class for both of, so on that one I'm not worried. But in kilonewton it was 2407.664 Newton. Now this was the total weight of the bridge deck, that one. Okay. Now to find the tension in this rope here, the T. Okay. We can either take moments at A there, with of course the equivalent weight, that one acting from the middle there. Okay, that's the weight of the acting from the middle. Then we can take moments at A to find that one. So if we take moments at A, you have something like, and the bridge deck is 52 meters long. So what we are going to have is something like, taking moments at A. So we are saying, okay, 2407.77. Now that's this would be negative times 52 over 2 should be equal to, no, not equal to, then this plus then we will have T sine 65 times 52 is equal to 0. So that's the moment, summation of moments about A. So that one, if you, oh sorry, 64 degrees. So when you do your thing here, you just find that your T is actually equal to the weight over 2, which is 1, the weight over 2 times that, which is 1339.44. By the way, it's kilonewton, sorry, kilonewtons there, don't forget, take note, 4428. This is kilonewton also. I hope. So that is the T we calculated for this part. So this one is the T which is there. Since that was the first calculation by the engineer, it was assumed that all the pulleys are free to rotate. So it will be the same T which will be here. It will be the same T here. It will be the same T which he calculated as to be put by the 3 cars. So it is that one there. Now we are told when he started pulling, this pulley D jammed and pulley F also jammed. So we had done the calculation, we drew the free body diagram there. So I'll just apply the formulas now for lifting. So we already know the tension here. It is the 1339.44. So we need to find our T DE, that's what I'll call it, TDE, and then I'll call this one TEF, and then we have the T we need now. So the TEF in this one here is the one we just calculated, the sort of the force required to lift the beam. So to find our TDE, we are saying, okay, since now the vehicles are the ones lifting, so it will be TDE is equal to the T which is here, which will act as the T1, which is the 1339.44 QH. Then E to the power mu. The mu between the rope and pulley D is 0.56, so put 0.56 multiplied by the beta now, the wrapping angle there, which we had calculated in class to be 116 pi over 180. So with that being said, we said, okay, then we'll find our TDE. So our TDE turned out to be, for me, it turned out to be 4, and you're gonna have to verify these things. 416.0993. Yes, that's my TDE. And then from here, we were told that pulley E still continued rotating. So the same TDE will be equal to TEF. So it will be the same equal to TEF. Since pulley E is rotating freely in the clockwise direction, it only cannot rotate in the reverse direction. So now, to find now the force T here, the T here which we need, we will have to repeat the same using that. So it will be now T will be equal to TDE or TEF, whatever, and then E to the power. Now we need the friction between pulley F, for pulley F and the rope. So pulley F and the rope, it is that one there, this one. So that's the one we put, which is 0.52, and then multiplied by the angle. The angle, it is entering at vertical and leaving at horizontal. So the angle is it's 90 degrees, which is in radians, pi by 2. So when we solve this, our T is coming out to be 9419.9899 kilonewtons. So me, I'm working in kilonewtons because of failure to write. So this is the answer for B. That's the answer for B. So you see, because the pulleys have jammed, they have to go to that. When the pulleys had not jammed, they were only required to do that. But the pulleys jammed, so to overcome friction, they had to go to 9,000 like that. Then so after they lift the beam now to the horizontal level, two cars were to leave to go get the material to backfill here, so that they backfill properly. And then one car was to remain holding the bridge horizontal. And then they put on that car the load there, because they are switching off the engine. So we want the minimum now. So now to get the minimum that is required, we allow the bridge deck to be the one which is pulling, so that we have just the minimum here. So the bridge deck will be the one pulling now. So we're gonna have to work it out. Now in the 06 class, I made a mistake on this one, so please pay attention. So what we see is that this will be pulling, and the force we had calculated is the 1339.4428 kilonewtons. So that force is what will be pulling now. So now we need to calculate the TDE in reverse. We need to calculate the EF in reverse, and then we need to calculate the T there finally, which then will vary. And remember, we are being asked for the minimum mass that the vehicle plus the luggage should have in order to do their intended work there. Okay? Alright. So that being said, we can do that. So we are saying, okay, so to get the TDE now, so we'll do it in reverse. So TDE will be equal to, it will be the tension here in dB, which is the 1339.4428 divided by E to the power the friction, which is 0.56, the coefficient of friction, times the 116 angle, and then pi over 1/8. So this gives us our TDE now. TDE in this case now is equal to, it is coming to 431.05819. Okay, so from here, and this, where we made the mistake in the morning, is that we did not consider that pulley, it does not go clockwise. So we say that because it does not go clockwise, and since the bridge is pulling, so this also now has to have friction at pulley E. So the calculated pulley DE will be the T1. Now we need to get will be the T2 now. We need to get the TEF, which will act as the T1. So TEF will be equal to, again, the 431.05819 over E. Now we need the coefficient of friction for the rope and pulley E, which is this one, 0.46. So 0.46, and then multiplied by the angle. Now it is entering horizontal and leaving vertical, so the angle is 90 degrees, which is actually pi by 2. With that being said, we find our TEF to be equal to 209 point. By the way, this is kilonewtons. Let's not forget 209.28078 kilonewtons. Okay, so this is now the force which is here. It is the force which is here in this one. So we need now to get our T there from there, because this also looks like it is more like a jammed thing. The pulley F, it's also a jammed thing. So that being said, you are saying, okay, getting our T now will do the same. It will be equal to the TEF now, which is the 209.28078 over E to the power. What is the coefficient of friction between the rope and pulley F? It's 0.52 multiplied by the angle, which is pi by 2. So with that being said, our T turned out to be 9, oh sorry, that's 92, then 0.4 468. Let's just end there. Kilonewtons, whatever. Okay. So that being the thing, this T, okay, is the one here. So the friction, which is of course, remember the T is pulling the car this side, so the friction should go this side. So this friction should be equal to the T. So this value here is also equal to the friction. So to find the normal force, we'll just say normal, which is the normal force, which is equal to the weight, should be equal to the friction force over mu. Okay, so it will be 92.468 over the mu between the tires and the ground, which is the 0.71 there. So over 0.71, which gives us okay, which gives us 1 3, that's a 3, 130.262. Come on. Okay, so okay, so 0.236 kilonewtons, like that. So 130.236, that is the weight, which is also the mass which is required. Oh, sorry, the weight. Now to get the mass, we just divide that weight by So mass will be equal to that 130 divide by 9.8. But because it's kilonewtons, I think I want kgs, so I'll multiply by 1000. So I'm saying 130, and then I will not 236 divide by 9.81, which is the gravity. This gives me the mass of 13,700 and 275 kg. 13,275 kg. It gives me that mass there. 13,275 kg. So that is the answer for C, this one. That's the answer for C. Okay. Alright, so moving on to the next part now. What we are told now, okay, now they do that, they backfill and whatever, and they insert the wedge. Then they say calculate the friction force on the top of the wedge when the rope is fully released, like there's no force in the rope. Okay, so they put that, then of course there's no force in the rope. I guess I was supposed to remove all these things, but anyhow, let's just have it like that. Let's just have it like that. Let's just have it like that. So with this, it is no big deal. What they want is for us to calculate the friction forces on the top of the wedge of the rope when the rope is fully released. So you will have this beam AB, a free body diagram probably will be like that. Okay, so here at A we are saying, okay, you are going to have there AX, AY. So that is AX, AY. Then here now, where the part which is sitting on the wedge, okay, we expect to have the normal like that, perpendicular to the incline of the wedge. So that is, let's call that N1. Okay, and then we are also having a friction. Now it is you to determine where does the friction, which direction will the friction go. Now remember, when you insert this, you drop this bridge deck on the wedge. The wedge will be moving outward this side. So it's like the wedge will be seeking to go this side. And relative motion will then make the bridge deck as if it is going this side. So the bridge deck on top there will be going this side. So the friction to oppose the relative motion of the bridge deck would definitely be going in this direction. That's how the friction will be moving. Now, we thought the horizontals here and the like, I think, and the verticals here. I think we have the wedge angle. The wedge angle is 32 degrees there. The wedge angle is 32 degrees. So for those of you who are intelligent, you know that is 32 degrees. And then that is also 32 degrees. Then the friction, we have a friction equation which we need to solve so that we relate the normal to the friction. So with the friction between the wedge and the slab, so the wedge and the slab, the friction is that 0.05. So then relating the normal to that with that coefficient of friction, so the friction force, this one, if I just point to it, so we are saying friction will be equal to 0.05 multiplied by the normal N1. That is the friction which is actually there. Alright, so remember that the weight of this thing was what we had calculated earlier. Even in class we had calculated. It turned out the total weight as in the whole, it turned out to be 2407.7, we'll round it off to that. So obviously we'll take moments at A here to get this normal thing going. Okay, so when we take moments at A, okay, at A, then we'll have clockwise moments negative. So we are saying summation of moments about A is equal to 0, implying that N1, I'm beginning with the normal itself, N1 cos 32 cos 32, okay, that's the y component. It should be times the whole 52, which is the length of the bridge, plus I need the y component of the friction, which is also positive, so it would be plus 0.05 N1. Now this would be sine 32. I'm just getting the y component of the friction which is going in that direction. So its y component is given by sine 32. So the friction force is 0.05 N1 sine 32. So this again we are multiplying it by 52 because it is acting at the end thing. Then minus half of the distance of 52 where the weight is acting, it will be 26, then times the overall weight, which is now 2407.77 is equal to 0. Okay, so this is the equation. With that being said, you can solve for N1. So when you solve, N1 should be equal to it's equal to 13 like that. So if that is our normal, then our friction force Fr is equal to 0.05 N1, which is equal to just 68.83, just rounding it off like that, kilonewtons. So I found the friction on the top. That is my D. This is the answer for D. This is the answer for D. Now friction at the bottom. Okay? So now we'll need to, instead of just getting the whatever, the wedge, we'll now need to draw the free body diagram for the wedge. So the free body diagram for the wedge now is like that, because that's how you can get at the bottom. So you have the normal here, which we'll call N2, which we are looking for. Then the weight of the wedge, which we have been given. Then on top here, we have the N1, again, which we know, and it's at 32 degrees there. So that is like 32 degrees. So this is N1. And then there's the friction also. Notice the friction has to go this side. So this is the friction, which is 0 0.05 N1, and it's also like that. So you see, on the bridge deck it is going up, on this one it is coming down, and that is logical because the wedge is being pulled outward, like it wants to come out, so friction should hold it inside. By the way, there's also friction at the bottom here. It is also going that direction, which is F. We'll just call it F2. Yeah, like that. Which we'll calculate, of course, we know our F2 is equal to also that coefficient of friction between the ground and the wedge is 0.28. So our F2 is equal to 0.28 N2. Right. I'm using my mouse for writing, so if somebody can, someone bought me a duster, if somebody can buy me a tablet. Since some of you guys have got money, you can do that and bring me a tablet. Yeah, I'm tired of this red ink. Can't I change to something a little more better? How do you change the color? Oh, okay. I don't know. Okay, we'll carry on. So I'll just write the equation here because now it will be just summation of forces in the y. So summation of forces in the y, it's like you have N2, which is at the bottom there. So that is our N2 there. Okay. Yeah, N2 then minus N1, that will be cos 32. Oh, come on. That is cos 32. And then minus the friction on top, it will be 0.05 N1 sine 32, and then the weight of the wedge itself will be a minus 23. All these should be equal to 0. So from this, when we solve for N2, we'll even get a smaller value than N1 because N1 was 1376. N2 is actually 1226.8832, something like that. Okay. So then the friction F2, which is the friction at the bottom, should be equal to, as we had 0.8 times N2, so it will be 0.28 N2, which is equal to which would be equal to 343.53 kilonewtons. So this is the friction at the bottom of the wedge. Then they ask a question lastly. Determine if the wedge is self-locking or not. Ooh, I can't believe time is flying this much. But but determine if the wedge is self-locking. Obviously, I need to compare. We see on the wedge here, the two friction forces have their x components in the negative, and then N1 is the one which is having a positive x component. So I need to compare those two. So if I say to determine whether it's self-locking, I'll say the x component of N1, which is N1 sine 32. Now this is the x component of N1 minus, then I lump the friction forces. So the friction forces, it will be the F1, which is the Ft, which is friction on the top, cos cos 32, which is the x component, and then plus the F2, which is below, which is just or the F bottom, which is the friction force at the bottom, like that. So now I'm saying, okay, if this expression gives me a positive, then the wedge is definitely not self-locking. Why? Because it means that the force N1 sine the x component in the positive, which is pushing the wedge away there, it means it is actually greater. If I get a negative of this expression, then I know the friction forces are sufficient and it is self-locking. Self-locking. Actually, there is no nothing actually. So from these two, this one N1 sine theta, you get 700 and something, 720 something kilonewtons. And then these ones, Ft cos whatever plus Fb, you just get 300 and something. 390 something, if I'm not mistaken. So from here, I'm able to determine that the wedge is not self-locking. So my wedge is not self-locking. And then the difference now between these two is the force I need to apply as P here, so that I balance this one. So the difference between these two, the P, was coming to 327. Uh, 0.5 kilonewtons. I think my computer is running out of memory. Something like that, kilonewtons. So please, I have solved it through using my values. It is due tomorrow. Everyone should solve for themselves with their own values. Yes, everyone should solve. I've solved, I've shown you. You have to watch this video and solve. Unfortunately, it is due tomorrow, and I'll be quite strict. I will not be there tomorrow, but I'll come back late in the afternoon, and then I'll also tomorrow. This assignment is due, and you must submit. Okay, you must submit. No, actually, it's not physical submission. It is on the form. So I'll just switch off the form by the end of by around 16 hours. I'll switch it off. So you must submit before 16 hours. Before 16 hours, because I'll switch it off and I do not want to be caught to say, no sir, can I submit whatever. Nonsense. I don't want to hear that. You're submitting tomorrow 16. By 16 you should have all submitted. Lazing around and the like. You can read the concluding remarks for the story there on your own. What else do I want to say? Follow the instructions in the form that you are submitting. Some of you I'm repeating my disappointment. Please do not disappoint me. Okay? When I say values, I mean only values. So when I look at your responses, some of you are putting units when I've said don't put units. I only want numbers. And I've guided you how you should be answering. So this one who did this is wrong. I didn't say put raw number. I just wanted the number. Hmm? So all of you, these who are putting degrees, I've said don't put degrees. You go put degrees. Nonsense. Next time I'll penalize you very much. So make sure you only put the number because I do not want to struggle. I've told you in what units it should be, but don't include the units. Okay? So all of you were putting this to my degrees, what and what. Nonsense. I hope for this other one also you not put the whatever things I'm not asking. Okay? Alright. What else? 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 I think that's all.